that we still have an increasing volume of data per user per time, and we are expecting that Internet of Things will increase the demand of, and traffic. And many technologies, and we probably care more about this, affect more our human lives, and they require very little latency, like safety, healthcare, education, defense, and also a more humane interaction when we are distant from each other. And of course, communication for space exploration. So I gave a few examples of all the combinations possible you can think of for free space optical communications. I'm going to move forward with that. Just to mention that there are a few, out of this world examples of free space optical communications that are currently occurring. And one of the most amazing ones probably will be the laser communication relay demonstration that is going to very soon connect the space station to the ground, to a Hawaii station, using a relay, LCRD satellite, and the part that is missing that is going to be installed pretty soon is the Illuma-T, this device here that is covered, that is going to be mounted on the space station. Okay, but now, because of the time, we are more concerned about terrestrial free space optical communications. This is a nice view of Santiago that you may not have not seen before, because it was taken in a pristine air. It's not always like this, but it improves, believe me, gets better, and it's getting better, I would say, every year. This is how it's going to look again in a few years when we solve all the contamination problem. But when we see this, we see an incredibly large opportunity for extending our data communication approaches, and laser communications, along with, in general, wireless optical communication systems, will need a lot of physicists, engineers, and people working on this area. So there are going to be jobs for us. Okay, this is important. So free space optical communications, is a point-to-point line of sight method that uses light for carrying the information data. This is a very simple example of a system like that. The most basic way of conveying the information would be changing a property of the light. And the easiest one is to change intensity. Yeah, the change of intensity would carry the digital information that we are trying to transmit from one point to another. And if we want to have full capacity of free space optical communications, we need to use not only incoherent intensity-based modulation formats, we need to move into coherent systems, because that's what is going to give us, the full potential of links like this, among other things that I will discuss briefly. Now, some of the challenges we keep having with FSO: beam acquisition and pointing and tracking, which is a mechanical problem; optical attenuation because of propagation, and also because of the components we are using for this; cloud cover and fog. I will mention something at the end, which is part of the atmosphere; angle of arrival fluctuations; beam fragmentation; loss of optical coherence. This is important for coherent communication; and the fact that we need to devise new signal modulation schemes and carrier multiplexing. And so atmospheric absorption is something that we always need to think of for beginning to think of a system like this. And the choice of wavelength affects both link's performance and detector sensitivity. So I've shown you here what you get out of the simulation system. I forgot the name. Is this software that allows you to have the transparency of the sky, Modtron. And I did this calculation for the typical situation in a summer time on Mediterranean latitudes, and you can see that wavelengths that we can usually use in our labs are possible windows for communications in the atmosphere. particularly 1550 nanometer, which is the wavelength that is used in fiber communications. So for that, we could have ideally a transparent connection between the two if we solve the other problems. But we also can use visible light for transmission across the atmosphere. The limitation would be in that case, the eye safety because of regulations, even though we still don't have written regulations in Chile. There are international regulations for the amount of power we can use because of the focus on the visible light in the eye, okay? But there are different wavelengths and regions where we can test different approaches. Fog continues to be an extremely difficult problem to solve, and this is a simulation where it shows that when you have very low visibility, is very doesn't make much difference whether you're using one wavelength or another. When the visibility is larger, you can find some differences, and 1550 nanometer seems to have a better transparency and in this regard. Okay, there are some efforts being worked in the lab, in some labs, on how to make a channel through the fog, but this is still something that is experimental, nothing developed yet. Okay, what about rain? Rain is more beneficial than fog, and if you've done experiments in this, you will see that the attenuation may be up to, say, 4 to 6 dBs per kilometer if you have moderate to strong rain, which is much better than what you would have in fog, which can reach up to 200 dBs per kilometer. So in an FSL system, you would expect, and I have a pointer here, if you start with a Gaussian beam on your transmitter side, on the collecting lens at the other end of the link, you would have everything distorted. Some part of the light obviously would be outside. The beam spot is larger than the receiver aperture, and it's going to be fragmented. On the detector side, so on the focal plane of the receiver, you would have a fragmented point spread function that is also dancing on it, and that is going to cause scintillation. So our channel is a randomly, some people say isotropic or maybe anisotropic if it is near the ground, anisotropic distribution channel. And so from the perspective of turbulence, I mentioned angle of arrival fluctuations, speed fragmentation, loss of spatial coherence. In these examples here, I show, what it looks like of the beam reaching the pupil of the receiver, and that will be the dancing of the beam of the focal plane. Certainly, if you have a small detector area, that is going to show significantly large fluctuations. And those fluctuations, these are experimental, by the way. So these are the kind of fluctuations you could get on your receiver because of a strong turbulence near the ground. And in this case, a scintillation index is 1. So you have deep fades here that are very difficult to counter, at least with just a simple system like that. So a good design needs to minimize the symbol error rate, and not only that, also increase the link availability. So it needs to be working all the time or most of the time, okay? And these are very dependent on the channel. So solution to improve this, yeah, people have mentioned in the past, aperture averaging, spatial diversity. That could be multi-path or best path, multi-mode. If you use specialty modes in laser beams, wavelength hop, that is only meaningful when you have a large wavelength separation, adaptive optics, pre and post compensation, modulation formats, and multi-hop links, something that Professor Gassemblui have done in his group, I remember. So one of the ideas is spatial diversity. So what if we have different beams on the transmitter side? So like a MISO system. Could we reduce the effect of scintillation? Could we reduce the number of the magnitude of those fluctuations to improve the quality of the detection? Well, that will depend on whether we have uncorrelation between the signals, the paths that are transmitting to the detector side, okay? So we need to ensure that the diversity, and that will depend on propagation length, turbulence strength, and beam separation. And in this plot that I showed here, you see, when you have a short distance, 1 kilometer link, you need shorter separation to achieve uncorrelated between the two paths. But as you increase the propagation distance, for example, here 9 kilometer, then you need a larger separation between the transmit beams in order to have that uncorrelation that you needed in order to reduce. Reduction, nevertheless, is not something that could mitigate totally the problem. You still have temporal fluctuations that I may address later if we have the time. Okay, one thing that inspired me to work experimentally with diversity was, for example, this work published that began later, much earlier than this, but the group led by Anton Zeilinger in Vienna using beams with orbital angular momentum, in this case, a very slow transmission rate system, only just to demonstrate the principle. And the beams wouldn't be detected by any detector, but just a camera that would be later on translated into a symbol just to demonstrate that you can transmit images. But it was a proof of principle. It was well published everywhere. So, but the way that we've seen this is, what if instead of using multiplexing, we use OAM for creating a different diversity, symbol diversity. So modulation using OAM. So we could pack, a sequence of binary bits together and define a symbol. So in order to do this, we need to select a large number of OAM states that is going to be our full set, and we can activate a few of those OAM states to form a symbol. That's the idea. These are examples that we did some years ago in the lab, superpositions of two OAM states, a negative and a positive, and they form different shapes. And those black lines you see in between are the phase cancellations that are produced because these are coherent superposition of OAM states. So lately, we've been building a test facility at the Universidad de los Andes. So what I'm showing you here at the engineering building that was built not long ago, we have in an office for now, it's going to be moved later, we have a folded system, propagation system. We have transmitter and receiver on one side, a remote system on the other, and about 500 meters away. So I'm not going to go through details. We don't have much time for that. And we're using visible light because in order to use telescopes, those that are off-the-shelf telescopes, they're coated with the coatings for visible light. If you want to use infrared light, you need to order your special coating, which is very, very expensive. So, but we'll be using something that is very practical, has been monolithic. We have designed a monolithic system that transmits a beacon for alignment, also for measuring the strength of the turbulence. And the big scope here is used for transmitting OAM states. So we expand the beams so that the diameter is sufficient so that we can have a compact diameter on the remote side and also on the side of the receiver. We currently produce OAM states and transmit OAM states up to topological charge 45, which is the amount about the maximum that you can get out of this tube here, 14 centimeters. Now, so the idea we're using polarization. So we print OAM using a spatial light modulator or SLMs. SLMs use a polarization alignment that is on the longer axis. So in this case, on horizontal axis. So in order to transmit both and have the ability to receive both signals, the beacon signal and the OAM signal on the same received telescope, we are rotating polarization. So the OEM is transmitted with horizontal polarization and the beacon with vertical polarization. We rotate that. And so on the receiver side, you will see this, this is remote station, 500 meters away. This is the beginning of the night. You can see some of the light there. The two mirrors are mounted on a gimbal mount that is controlled remotely. The mirrors are not very large. These are 4-inch mirrors, so 10 centimeters each. So we need to focus the light, the beam on the mirror. The focal point, of course, at that propagation distance is very large, so that we can have a matching diameter on the receiver side. That's a short video that I show the amount of turbulence we can see. This is seen from the transmit side. So maybe from afar you don't see all the turbulence, but it's very strong. Now, on the receiver side, we've mounted a 2-branch receiver, also monolithic, that is here, so that we could have the OEM that is entering this Schmidt-Cassegrain telescope, and inside it is split, the signal that is measured for turbulence strength determination, and also for recording data, different kinds, and high-speed cameras, and the OEM. Now, since we are interested in communications and using modulation, we are trying to find a good systematic way of detecting the topological charge of the OEM beams. And now we're using a shock Harman sensor, okay? In order to do this, we need to compress. Imagine this, we have a large beam. We cannot analyze a large beam. We need to do a compression. In this case, we're using 55-time compression, so that at the output of the oscilloscope, after the eyepiece, we get about a diameter of the order of 3 to 5 millimeters. We are currently not using any adaptive optic point, even though we are working on that idea. So just a quick example of what you could see. I'm holding a piece of paper here in front of the receive telescope, so that you can see both the OEM, very distorted, and the beacon that is also very fragmented, that both entering the receive telescope. And these are typical OEMs, single state OEMs, one that is nicely, disturbed, and the other one harshly distorted by the turbulence. That's the kind of thing we're receiving, and even though the strength of the turbulence, as I'll show you in a second, we can still decode the content of the topological charge and distinguish them. So briefly, I'll describe one of the things we've done for detecting or measuring the strength of the turbulence. We're currently using two systems. We're using a position sensing device that allows us to record the point dancing on the surface of this. So you can see here, this is the image dance produced by the centroid of the beacon, dancing all around, and the diameters are varying depending on the strength of the turbulence. So the larger the turbulence, the more the dancing. This is related directly to the angle of arrival fluctuations, okay? So these are the intensity fluctuations seen by those, by another point detector, and these are the centroids dancing on the X and Y axis. What we always have is temporal correlation, of course. This is an important aspect of this. In this case, it was because we have a kind of a stronger wind. We have a correlation time of 6 milliseconds. It could vary from 2 to up to, when it's very slow and quiet, 20 milliseconds, the correlation time or the characteristic time, okay? So from that, we get an estimation of CN squared, which is one of the ways to represent the strength of the turbulence. Well, this is not all, because when you're transmitting, you need to know the propagation distance. So you can transform this or use this to put it in terms of the Fried parameter, for example, or R over D. So these are the measured CN squared values that we have obtained in one of the campaigns. The values are really, really strong. We are about 15 meters above the ground, passing through 2 roofs of large buildings that are accumulating heat during the day. So we usually use this in the evening. So the strength of the turbulence varies in this case. So in the order of, say, a fraction of 5 or 4 times 10 to the minus 13 up to, say, 4 times 10 to the minus 12 is very large. These are two examples. These were performed before. This is a shorter distance, but so that you can see what happens when you transmit a coherent superposition of two OEM states, these minus 20 and 20, minus 30 and 30. Of course, these are recorded with a fast, high-speed camera, 1,000 frames per second. So the speed here is reduced like 30 times. Okay, in reality, this is much faster. This is nice. This is what we would like to expect. This is not the reality most of the time. But the idea is we want to have a detection with a shock Harman sensor. Why this? Is a possibility. We've worked with also with the other device, the mode sorter, developed by an approximation of that, developed by the Glasgow group. And we realized that this is very practical. We already had a shock Harman for adaptive optics. And so we're reducing the number of subapertures. I don't have time here to describe the purpose. You can find this on some of our publications. But the idea is that vortex beams, because of the wavefront that it has, it projects spots that are away from the central of the subapertures. For a plane wave, you have all the spots on the central parts of the subapertures. If you have this wavefront that is rotated, that is inclined, then those spots are going to shift. And that shifting is proportional to the topological charge. Now we devised a method that is we call local OAM. I'll say something in a moment. But look at this. These are the kind of recordings we're getting. The area here is 5 millimeters. Okay, so OAM state 15, 25, 40. Look at the even though this is not an intensity, this is not a camera image, just the spot from the shock Harman sensor. But you can see that they distorted, they are off center, they are unbalanced in terms of intensity, and we can still derive the values. We're using in practice 17 by 17 subapertures, each with 60 by 60 pixels. Calibrating this takes some time. Once you learn how to do this, it works very nicely. But it took us some months to do it at the beginning. Okay, this is an example of an intensity field that we're looking at. Okay, this is the kind of distortion we're getting. This is with the high-speed camera. Now, I'm going to finish with this maybe. Not time for quantum part. But if we produce this local OAM map that is multiplied by the intensity image coming from the shock Harman, you can find it on our publication. We can produce a histogram, OAM histogram of values. Even for a system without any turbulence, it's going to produce an extended histogram. Okay, because each and every point we're not calculating the centroid, because the point could be totally fragmented. It wouldn't work when you have strong turbulence. So we calculate the OAM contribution for each and every pixel that is illuminated. We multiply this local OAM map that is calculated once only for the system, and we get this histogram. One easy way, when you have a single OAM state in the light, you simply calculate this. It's a simple weighted average, and you get the OAM state you're looking for. Is it accurate? It is. I'm now redoing everything in the lab without turbulence to show that this is very, very accurate. So the amount of deviation is less than 0.1. So this is an example. OAM state 30 transmitted over a very strong path, 6 times 10 to the minus 13. And the estimated value after that, applying that formula was 30.5. We do this with many images. in this case, 400 different images, okay? Uncorrelated images on the same time of the day, of course. And this is the histogram we get. So this is the quality of detection we're getting by doing this with this method. And this is an example of this situation. It's actually in the same recording. We don't need to have a center OEM beam on the plane in order to get the accurate. So more examples. I won't stop here because it doesn't matter. Just the idea that the quality of the detection varies. We don't understand exactly everything that is going on. We're still learning about this, but nevertheless, we are trying to find the narrowest standard deviation of all the detection we get from the images, 400 images each, because the better this is, the higher density of OEM state we can have within a range, right? I'm gonna skip this, maybe this one here, and that shows how much the turbulence is varying in terms of the incursion of the beacon spot on the plane. So this would be strength of turbulence in a way, and this would be OEM spread. And it varies depending on the kind of OEM that we're testing. So I'm not making any claim yet, but it seems that it matters the sizes of the scales of the turbulence in terms with respect to the sizes of the diameters of the OEM state we're trying. And this is just when we compare scintillation index, which is kind of a more standard comparison. So this, we have two OEM state together, coherently superimposed. This is the histogram of one of the images, and these are the histogram of 400 or 200, I forgot this, of all the images, showing clearly that we can detect the two superimposed OEM states, regardless of the strength of the turbulence. Yeah, I don't think we ran out of time, right? Okay, just one thing that this is just I put it just because I like the picture. Maybe some of you have seen it. Yeah, this is the free space link, quantum space link between the Tenerife and La Palma, Canary Island, by the group led by Anton Zeilinger. They've been working on this with other people that I haven't met yet. So they have a nice experiment to show that, because the idea of quantum transmission of quantum states will be something interesting. Some people claim that, oh, we don't need this yet. With the increase in capacity of the quantum computers and eventually their connection to our networks, this could be relevant if we want to have secure communications. And so I find this a very nice approach and show how we can use entangled states. So entangled states, for those who don't know, is having two photons that are generated with the same source on a nonlinear crystal that have properties that are inseparable. So if you modify one of them with one quantum information, the other one, regardless of its location, is going to be modified accordingly. So I'll skip this, but I'll show you that. So we are also working in spatial diversity for quantum transmission, and we are being helped by the Quantum Future Group in Universidad di Padua. We have designed a system that the idea of using diversity, which is something common and known in classical FSO systems, we try to do it with quantum, which is a different story, because when you are transmitting a single photon, then you don't use the two paths, you use one of them. So what we're trying to do here is select the best path every time by checking with a beacon how's behaving. So this is one transmitter. So we have a beacon here with a dichroic mirror, This is the quantum signal on green using an off-axis mirror so that the beacon here at the end, they're collimated. It's kind of tricky to do in the lab, but we have done it. And now if we have two of those transmitters and we have one receiver, we could do this detection, and with the system on the receiver side, we can check every other millisecond how's the quality of the channel and send a feedback signal to the transmitter. Since we're doing this with pulses, we need to know which of the channel it is because we have one receiver on this side. So we use just a simple delay with optical fiber so that we can have one pulse that is, you know, in the order of 2 nanoseconds and the following one 10 nanoseconds later. And that's the way we can distinguish the two of them to know which channel it is. So it's been tricky. We're doing this in the lab only, not yet outside, but that's the plan. This is a build system. So the idea is that we can separate the two transmitters apart to find the the position where they are actually uncorrelated. And this is the receiver side. And one important thing, can we trust the beacon to see if this is going to be working for the quantum domain? Yeah, we found that in the lab that the correlation is 0.8, so close enough so that we can use this. But we will see what happens outside. And it's going to require the help of our friends in Italy. And that's the gang, the group. Most of them have graduated here. These are the PhD students and postdoc that recently joined that is going to work in adaptive optics. And our PhD program and master's program is always open for interested and motivated students who would like to work in theory and, of course, in experimental demonstrations. So thank you so much.
In order to keep our program, I offer 2 questions. Someone want to ask? Another question? The last one?
Classical density modulation direct detection is quite depending on the device's bandwidth. So the quantum is the similar case.
Yeah, people still starting to work with the detection that is fast enough. So speed is not something that is at this point. The first application is the low hanging fruit. Speeding. That is
Excellent, Professor. So I started working on FSO about 10 years back with Ferry as PhD student, and we have done a lot of experimentation on turbulence and fog. We saw the similar situation for intensity modulation, direct detection, yeah. But you have done a great work in turbulence. Do you have done some work on in foggy attenuated channels as well? Okay. So what's your comments on that? I mean, that is the challenge that we can.
Guiding channel, half a meter long, with the intensity, with the information signal low in the channel by the dissipated fog from this high power. Grading the tunnel. Exactly. It is. Like a horrible fight. Yeah. Like a horrible fight.
Please keep some minutes. I will invite Farid here because the organization wants to recognize the valuable work and research of Isaman. Iceman, you? Osman, sorry.
I think it's a presentation about our keynote speaker. Unfortunately, the stand couldn't be here, but we will take it there. In the organizing committee, I've got some people to say thank you. I mean, these guys have put a lot of effort and shared the phone of appreciation. Some people, and also.
No.
Yeah.
No, it's so, of course, to hide.
Yes, I mean, no, you're the CD. Yes, this is, you have to hear plays a hero. Yes, I don't know what it is, but I'm yeah. I just want to say thank you very much. Yes, for being here and for sharing this. Thank you so much. And then this is for Osman. Osman, this is your first gift from our organizing committee, and we wish you the very best. You are the youngest. Normally, I think this conference we have two copies. Someone just before the table. So we have to keep that back there. Thank you so much. Coffee. Yes, there is a coffee. This is the only conference I've seen that they keep you here for hours. They give you coffee after
15 minutes coffee.